before we can proceed on to the next topic. So there's something called the squeeze theorem, which I might have written down. Nope, that's fine. So the next thing we need is the squeeze theorem. Okay. This is extremely important for reasons that either will become obvious or sooner or later. Like, why is this so important? I think maybe it'll be more that it becomes obvious later. So if you go to the textbook and you just go to this section 2.3 and look for the squeeze theorem, you'll find it. It's theorem 2.7 in the textbook. Okay. But I'll give you the theorem here, and then we'll go into using it. Look at some examples of what do you do with this, and then we'll do an example that's extremely important. Like, why are we doing this theorem for just a couple of examples? Well, one of the examples is very important. We need it for chapter 3. So basically, here's just the concept in a picture, and then I'll give you the formal statement. If you have, say, some function, let's call this, I'll use the same lettering that the textbook uses. I'll use F, G, and H. So let's say you have some function H, like that, right? And you have some function F. Say like that. So here's H, here's F. And you have some other function that is stuck between them. It can be as crazy as you want. Oh, draw out the side of the lines there. You can be doing whatever, but it's between F and G. And maybe F and G are, or sorry, rather, G is between F and H. Maybe F and H are easier to deal with, like you know how to handle them for limits. So here's A, right? So if you know the limit for H and you know the limit for F, and they agree, they're the same limit, well, since G is stuck between them, it would also have to have the same limit. So for 3 functions, F, G, and H, if, and let's say 3 functions defined on an interval containing the number A. Defined on an, well, let's say open interval. We'll talk more about what open means in the next section. I'll say what it is, but we'll talk more about it in the next section as well. Define on an open interval containing A. If for all x in the interval except possibly A. Possibly A itself. And in the diagram, I'll indicate what that means after I've written it out. If for all in the interval, f of x is less than or equal to g of x, and it in turn is less than or equal to h of x, and the limit as x goes to a of f of x equals L, some limit, whatever that number is, the limit has to exist, and that's also equal to the limit as x goes to a of h of x, right? The limits of f and h agree. Then we can conclude that the limit as x goes to a of g of x also equals L. Okay, it exists and it's equal to that same number. So on the diagram, maybe we have some interval like right here, and x has to live somewhere in that interval, either side of it, and x could be equal to a. The x down here where this inequality holds, that f is always less than or equal to g and g is always less than or equal to h, that holds in that interval. It doesn't have to happen everywhere. In fact, what we could have is that somewhere over here, maybe we get this. Maybe over here, G then dips below F. But it's outside of this interval that we're focused on. Right? There's an interval around A where G is stuck between F and H. But at other places, it doesn't have to be. Just within the interval we're talking about. Okay. If G dips out around A, well, then this doesn't work. It has to be stuck between nearby that point. And what do I mean by nearby? We talked before. What does it mean for x to be close to 2? Same idea. Nearby. Same idea. This interval containing A, but not necessarily including A, is called a neighborhood. That's the technical term, and hopefully it makes sense. It's called a neighborhood of A, or a neighborhood around A. And it does not necessarily include A. A could be in the neighborhood, but it doesn't have to be. So if you think about it, and why is this word chosen? Sometimes in math, it's not clear why the words are chosen what they are. Like when you say an open interval, what does open mean? We'll talk about in a second. So a neighborhood of A, think about it this way. In your neighborhood, wherever you live, if you live in an apartment complex, you might just think of the apartment complex as a whole being the neighborhood. But like, I live in a house, so the neighborhood is, people, how other houses nearby, right? So if say my friend calls me, and like he's gonna come over to my house or something, he's like, "Oh, are you at your house yet?" And I go, "Oh, I'm in the neighborhood." That's telling him I'm not at home, right? I'm saying no, I'm nearby, right? I'll be there in a few minutes, right? If I was actually at home and my friend calls me and he goes, "Oh, are you at home yet?" And I go, "I'm in the neighborhood." Well, that wouldn't be quite honest. I mean, you could say, no, actually, technically, you're within the boundaries of your neighborhood. Yeah, but that's not what you wouldn't say it that way. If you were in your house, you would just say, yes, I'm at home, right? So when you say I'm in the neighborhood, that means you're close by, but not the place. So that's the same concept here. X is close to A, but not necessarily equal to A. Okay? Remember, going back to what we've been talking about this whole time, the whole point of a limit is what is the behavior nearby the number that you care about. Not at that number, right? Because sometimes that doesn't work. You get an indeterminate form, but nearby. So this whole time we're talking about being nearby, really it's the concept of a neighborhood we've been talking about. And again, that is the technical term. So something that we need to make sure is totally clear. Not because it's going to end up causing a problem for the way we solve these problems, but this is frozen again. Okay, not because the interval being opened or not open will cause us a problem necessarily in these examples, but that's what the statement of the theorem says. It's you have to have an open interval, and then later it will become very important whether or not our interval is open or closed becomes very important. So an open interval is one which does, again, this is another topic we could spend weeks on, just this topic really. But I'll give you the 30-second version. Basically, an open interval is one which does not contain its endpoints, right? So if I say the interval, zoom in here. If I say the interval, yeah, it'll work. From like 2 to 3, that is open, right? It does not contain the endpoints. If I say the interval from 2 to 3, including 2, that is not open. It's not closed either. If I had the interval from 2 to 3, including 3, that's closed. This middle one, some books won't name it at all. Others will say it's half open. Others will say it's clopen, a bit of a portmanteau of closed and open. We'll just not really give it a name. It's just not open. So for certain theorems, you have to have an open interval. For other theorems, just any interval will work. Any of these three are totally fine. And for other theorems, you have to have a closed interval. So throughout this course, it's going to become very important to always pay attention. What kind of interval do we have? Are we including the endpoints or not? Because that will affect which problem-solving techniques we use. So, for example, in Chapter 4, when you go to look at optimization, like maximizing a function, find the maximum point. Like if you're trying to maximize profit, or if you're trying to maximize the yield of something, or you're trying to minimize the cost of something, or minimize the materials used, then if you have a closed interval, then what's called the extreme value theorem will work. If you have an open interval, you need to use what's called the critical point theorem. So which theorem applies depends on the kind of interval that you have. So it's very important to always be aware of that. So zooming back out. Sorry, give me a second. Someone from Indiana is calling me. I'm not answering, of course. I just had to silence my phone. So, what example should we do first? Yeah, let's do this one. And there's actually one that's very important. We won't do that one first because I want you to get the overall concept down, and then we'll do the one that's very important. So let's do the limit. Yeah, let's do this one. Oops. Oh, you know what? Let's do this. This one I've done before. Sorry, just give me a second. I'm looking for a specific example. I just want to make sure that I don't do the wrong one. Okay, yeah, okay, cool. So let's do this one. The limit is x goes to 0 of x squared times sine of 1 over x. Okay? So, this example we actually haven't looked at yet. So let's examine this guy separate from the x squared first. So if you graph 1 over sine of 1 over x rather, then you get something like this. So here's y equals 1, here's y equals negative 1. Here's, say, negative pi, here's, say, pi. Here's pi over 2, and here's negative pi over 2. And in fact, I won't erase this. I'll leave this all here. So sine of negative pi is 0. Sine of negative pi over 2 is negative 1. Okay. Oh, I'm sorry. I'm doing this wrong. I actually don't really need those labeled at all. But you know what? Let's get rid of those labels. I don't need them. I forgot for a second, of course, that this is sine of the reciprocal of the input. I'll just do it a little more generally without trying to be specific. So basically it looks something like this. Because you're doing sine of the reciprocal, as you get closer and closer to 0, it oscillates faster and faster. And on the other side, same thing. Okay? Because you're doing sine of 1 over 0. Okay? So, well, not sine of 1 over 0, rather. Sine of 1 over x. X is going to 0. So the 1 over 0, is undefined. But 1 over x, as x goes to 0, is one we talked about before, is infinity. Oops. Just 1 over x, sorry. From the right, specifically, right? And then from the left would be negative infinity. So this doesn't really work because you get this. You can't just do the limit of the sine of 1 over x. This does not exist. As x goes to 0, sine 1 over x doesn't exist. Why do I bring this up? Well, if I take the same problem, copy it down here. Some people will look at this and go, oh, well, if you plug in 0, you're going to have 0 times sine of whatever. That's 0. Some people go, oh, it's 0. Easy. Well, that doesn't work because if you do that, then you're cutting corners and you're not recognizing that what you're really doing in that situation is you're applying the product rule for limits. right? You're trying to say, oh, well, I'll just do these two things separately, which you usually can do. There is a product rule for limits. But, and some of you might already have in mind what I'm going to say about this. The product rule only applies when the two individual limits exist. So the left one does. Limit as x goes to 0 of x squared is 0. True. But this one does not, right? We just got done talking about this. It's called an oscillating limit. It doesn't exist because the graph bounces up and down too fast. It doesn't settle on a single value. So you can't apply the product rule. This doesn't work. Product rule does not apply. So the fact that this is 0 when you plug in 0 doesn't matter. It's irrelevant to the problem. Because, again, you cannot apply the product rule here. So what do we do? Well, we're going to use the squeeze theorem. I want the limit of this function. Now I know the range of the sine function. I know, from the graph especially, I told you this is a height level 1 and this is height level -1. The graph bounces between those two values, right? So I know that sine of 1 over x is less than or equal to 1, simultaneously greater than or equal to -1. Okay, it's stuck between those two, right? That's just the range of the sine function. We're starting to build an inequality that puts the function we care about in between two easier to deal with functions. Okay, so you have to build this inequality yourself. I haven't double checked. At least last year in web work, we had some problems dealing with the squeeze theorem. I don't know if they're in the homework for 2.3. I didn't put together that assignment. Another instructor did. I'm reusing what they've already prepared. So I haven't checked if that's in there or not. It may be. Again, as I said earlier, when I go double check whether or not I need to adjust the due date, this is one of the things I'll look at. Anyway, now I can multiply each component. Oh, and by the way, since we started about 6 minutes late, I'm going to go over by about 6 minutes, so we'll be stopping at 12:20. So I can multiply x squared on each component. And since x squared is positive, right, I don't have to worry about the inequality changing direction because I'm multiplying by a positive value. So this is negative x is less than or equal to x squared times sine of 1 over x less than or equal to x squared. Can anyone tell me what's the limit? Oh, I forgot. Negative x squared, sorry. Can anyone tell me the limit as x goes to 0 of negative x squared? Anyone?
0, I think.
Yeah, because this is a polynomial, we just plug it in. How about this guy?
Also 0.
Yeah, also 0. We just plug in because they're polynomials. So essentially what I can do, hold on. Sorry, I had to clear my throat there. I'm essentially applying the limit to each component. So on the left we have 0, and on the right we have 0. So the limit as x goes to 0 of x squared times sine of 1 over x is stuck between 0 and 0. Therefore, it must equal 0, right? Like what number would be both less than or equal to 0 and greater than or equal to 0? Well, that would be 0. So we conclude that the limit as x goes to 0 of x squared times sine of 1 over x equals 0.